Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson for Design 1, we're going to be doing pinch analysis the way that the Learn Chemie videotapes did, but for the textbook example 15.2, just simply so that you can compare and contrast the two techniques. Let's look at the given information for example 15.2. They define the approach temperature to be 10 degrees C, and they have 6 streams. The m dot C sub P, they were given separately, but if you multiply them together, those are in the table here. The inlet and the outlet temperature are designated as T source and T target. And then the heat transfer is found by m dot C sub P times the delta T. And so all of this information is given in the book. Now the first step that we want to do is we want to do adjusted source and target temperatures. And to do that for all of the hot streams, and we can rename these H1, H2, H3, and these ones that are warming up are cold 1, cold 2, and cold 3. And for each of the hot streams, we're going to subtract 10 degrees C. So this is 290, 140, 190, 140, 40, and 40. For the cold streams, we don't need to make any changes. Okay? So those are our adjusted temperatures. Now we're going to use these adjusted temperatures to build a temperature interval chart. So I've listed the temperatures down along the one side, one for each line. I find it easiest to use the lines on paper. And then I've drawn or listed all the streams across the top here. And all I'm going to do is draw arrows. So stream 1 starts at 290, starts at 290 and ends at 140. One starts at 140 and ends at 40. Starts at 190, ends at 40. Starts at 190, ends at 290. Starts at 90, ends at 190, and starts at 40, ends at 190. All right, so then the next thing we want to do is we want to calculate the Q. Now to calculate Q, what we're going to do is use the sum of the m dot C sub P's, which I haven't written in here, but I can, 8, 2, 3, 5, 8, and 4. So we're going to add up the m dot C sub P's for the intervals, and these are negatives on the cold, right? We're taking heat out. And then I'm going to multiply that times the delta T for the interval. So this will be how I'll calculate the net Q. And when I do that, for this first interval here, I have this stream and this stream. So the sum of m dot C sub P is 8 minus 5. My delta T is 100. So 8 minus 5 is 3 times 100 is 300. And so this interval, the Q is 300. For this next interval, I have 8 plus 3, so 11. Okay, and then minus 8, so back to 3, minus 4, so minus 1. The delta T is 50, so minus 1 times 50 is minus 50. And we keep doing this. I have 2 plus 3, minus 8, minus 4. That turns out to be what? Negative 350. And for the last one, 2 and 3 minus 4, so positive 50. So I have all of my Q's. Then I want to do a residual. The first pass on this, we do it using a 0 as my starting point. So 0 plus 300, 300 plus negative 50, 250 minus 350, negative 100 plus 50. And then the next step is to look for the largest negative or the most negative. And so that would be this term here. And so this will be my actual residuals here, but I'm going to start by having heat addition so that I never go negative. So I'm going to start with 100. So opposite sign there. This is going to be my hot utility need. And then I'm going to add 100 plus 300, 400 plus negative 50, 350 plus negative 350, 0 plus 50. And so now then my smallest point is 0. And this tells me that this is going to be my pinch. Okay, so I've identified the pinch during doing this technique. And next what I want to do is look at the pinch analysis. So I'm going to separate this out into hot side and cold side. Okay, so we've identified the pinch to be 90 degrees C. Now that's for the cold streams. Remember that I had subtracted 10 degrees for the hot streams. I want to return now to the actual temperatures, and so I'm going to add the approach temperature to this. So adding 10 makes it 100 degrees C is going to be the pinch for the hot streams. And now then what I want to do is just kind of draw straight lines across for each of my streams. So if I clear out a pinch region here, and I've identified it for the cold streams as 90 degrees C and the hot streams as 100 degrees C, then what I'm going to do is I'm going to draw an arrow going from left to right or right to left for each of my streams. All right, I've drawn in each of our streams. I tried to sort of put them not really scaled, but at least left, right adjusted so that you can see where temperatures start and stop. The red streams are the hot ones, the cold streams are in white. And what I've need to do next is to go through and write in, okay, and the m.ccp's. So they're just written here down the center column in the pinch region, just out of the way. So now then, what I want to do is I want to analyze each side individually. So I'm going to start by doing the cold side of the pinch because it is easier. And I can look for what the Q is for each one of these. So for this one, it's 2 times 100 minus 50. And so 100 kilowatts. Similarly, we get 150 for stream H3 and 200 for stream C3. Now remember, this is just for the cold side of the pinch. Now the other thing that we need to keep in mind is that on this side, I need to guarantee that CC is greater than CH. So 4 is greater than both 3 and 2, so I can do any combination of streams here. So now then I just need to pick a stream. Which one do I want to do first? And it kind of doesn't really matter. If I do with stream 3 and 6 first, your choice of which way you want to do this. I'll be able to do all of the 150, but I will not be able to get all the way on the 200 here. So I'll only be able to remove 150 kilowatts. So I need to figure out what that temperature is. So if T minus 40 times 4 is going to equal 150, then I need T to be 77.5. So I'll be able to go from 40 to 77.5. So now then I need to go from 77.5 to 90. That's going to be another 50 kilowatts. I can now pair that with the upper stream. Now that will completely heat up stream C3, but will it do the adequate cooling for stream H2? Well, no, it's only going to do 50 kilowatts. So again, I need to figure out what the exit temperature will be from this exchanger. And so therefore, if I set 50 kilowatts equal to 2 times 100 minus T, it doesn't really matter which one you do. But if I do this, then let's see, 25 is 100 minus T. T is going to be 75 degrees C. So it will cool this side from down to 75 degrees C. And then I will need a cooler to remove the last 50 kilowatts. So there's my cold utility, and I have 2 heat exchangers. So 2 heat exchangers plus 1 cooler for this side. Now let's look at the other side. And on this side, what I need to guarantee that CH is greater than or equal to CC. So this is going to limit my pairings somewhat. Plus I have some temperature issues that will limit my pairings. So for instance, I can pair stream H1 with any of the cold streams, but I cannot pair streams H2 or H3 with any because those CHs are colder or lower than all of these others. So I'm going to have to do a cooling utility here and a cooling utility here. I have no choice. Based on this, I can work with stream H1, however. And so I'll start with the hottest because I want to pair the 2 hot streams together because that will take me from 300 down to some final temperature here. Now if I look and calculate the Q's for each of these, I can see that from stream C1 I can use 500 kilowatts to lower the temperature for stream H1. And so 500 kilowatts here. This will be complete. 500 kilowatts is going to be 8 times 300 minus the exit temperature from this exchanger. And so that exit temperature, 237.5. Okay, so stream C1 is complete, but stream H1 is only partially cooled. I have 700 kilowatts still remaining to need to be removed, and so I can do this by pairing with stream C2. Okay, and so 700 kilowatts, this one will be complete, but this is still going to have 100 kilowatts remaining. So 700 kilowatts is going to be 8 times 190 minus T 102.5 degrees C, so this will be 102.5 degrees C. Okay, and I don't have any other streams that I can pair with this, so I will need to do heating here. I will need 100 kilowatts of heat, and on this one I'm going to need 400 kilowatts, and up here I need a 300 kilowatt cooler and a 100 kilowatt cooler. So I'm going to have 2 heat exchangers and 2, let me clean that up, 2 heaters and 2 coolers. So it's not exactly the same answer as they got in the book, but it's very, very close. I could have done these pairings in different ways and gotten various answers. So this concludes this video lesson. Thank you very much for your time. Starting with 40